Let's continue ZAERO Advanced Training, Section 6, Bulk Data Cards and the Numerical Examples of Discrete Gusts. So we'll begin with Section 6.1, Bulk Data Input for the Discrete Gust. So this is an overview of the bulk data cards required for the gust response analysis. So to note, it's required to include the GenGust executive control command bulk data card in the executive control section, illustrated here. This will tell ZAERO to generate the gust aerodynamics in the AIC matrix. Because generating those aerodynamics takes extra time, by default the gust aerodynamics are not generated. So by specifying the GenGust card in the executive control section, that will trigger ZAERO to generate those gust aerodynamics. Also, if you're saving an AIC matrix for later use, you want to make sure when you originally generate the AIC matrix to include that GenGust command, and then the gust aerodynamics will be saved on the AIC matrix. So if you forget to do that, you're just going to have to regenerate the AIC matrix with the GenGust command present. So the default gust velocity direction is in the vertical gust. So to change the gust direction, you can use the GenGust bulk data card. The GenGust bulk data card can also be used to specify the best gust reference point for enhancing the accuracy of the RFA for the gust gaffs. So then in the case control section, you'll have a Gloads card to specify the gust analysis, which will refer to the Gloads bulk data card. And then this refers to the further bulk data cards to define the gust analysis. Additionally, here we have the plot time bulk data card, which allows you for post-processing of the transient analysis. You can visualize how the aircraft deforms in response to the gust. And we've seen most of these other bulk data cards. The new cards we'll talk about here in the section of the C-Gust and D-Gust cards. Okay, so this is an example of the bulk data cards that we would use in a state space approach. So we have the Gloads bulk data card, and then we have the rigid body reduction bulk data card to clean up the rigid body modes. The Gloads card, then, much like the ASC bulk data card, refers to the flutter and MNStack. The flutter card to define the analysis parameters, and then the MNStack card to define the RFA parameters. Also, we can refer to the ASC controller card to define a control system. So two examples here. We have CISO elements of a classic control system. So you can see we've got multiple CISO TF elements here defining a closed loop controller. So we have an ASC sensor feeding into our controller, feeding back to our actuators. Here's a MIMO element H infinity control system. So in a similar way, we've got the ASC sensor feeding into the controller, but now it's just a single MIMO SS feeding back to two actuators. For an open loop plant model, we have an ASC controller only referring to the surf set and sense set, which defines our control surfaces and sensors. So in this case, we have no control system feeding back to the system. The new cards, we have the D-Gust card to define the gust parameters, and then we have the MLD time to define the time parameters of time integration during simulation, and the MLD print card to output parameters of interest from the time simulation. So here is the Gloads card. So this defines the control system, the aeroelastic system, the airframe states, the discrete gust profile, and the time integration for the transient discrete gust loads analysis, or parameters for the continuous gust response analysis, which we'll see in the next section. So we have an ID field, which is the unique set identification number. The con ID field refers to an ASC controller card for specifying parameters of the control system. The flut ID field refers to a flutter bulk data card, which specifies the analysis parameters. The RAA ID field specifies the method of the gust response analysis and refers to a MNStack card. So if RAA ID is 0 or blank, then we do a frequency domain analysis, and so no rational function approximation is required. for RAA ID is greater than 0, then we use the hybrid method. So the RAA ID field refers to the MNStack card. This is for the rational function approximation for the normal modes and control surface modes. But remember, with the hybrid method, the Gust aerodynamics are solved through the frequency domain. And then lastly, if RAA ID is less than 0, the state space method is applied. So the absolute value of this field refers to the ID number of the MNStack card. So in this case, the RFA is applied to the control surface modes, the normal modes, and the Gust modes. Next, the states field refers to the MNStack card for airframe states. The ID Gust field refers to either a dgust card for the discrete Gust profile, which we're talking about in this section, or it can refer to the cgust card specifying the continuous Gust parameters. The time field refers to the MLD-time card to specify the time integration parameters. The MLD-print field refers to the MLD-print bulk data card. And then in the next fields, you can save and acquire some of the Gust aerodynamics. So the first save field can be save or acquire to save or retrieve the interpolated generalized Gust aerodynamics. And then we have a form field to specify the format of that saved data. It can be either format or unform for either ASCII or binary file. And then file name is the name of the data file. And then next, you can save the frequency domain. So save FRQ is for the discrete Gust analysis using the frequency domain method. Save frequency can be character string either save or acquire. And then file FRQ is the file name. So this stores the inverse of the frequency domain system matrix computed by the frequency domain method, or the time domain aerodynamic gust forces computed by the hybrid method. So in this case, if you're doing multiple analyses, you can save the data on the first run and then retrieve the data for subsequent runs. Next, we'll review the MNStack card and only the new fields required for Gust. So we have all the normal fields at the beginning, and at the very end we have 2 additional fields for Gust. So remember, when you have Gust RFA, we have a modified Gust RFA, which applies different parameters for the Gust rational function approximation. So these 2 new fields allow you to do that. So if we go to the next slide here, we can see that lag IDG is the identification number of an aero lag card to specify the approximation routes for the generalized aerodynamic force matrix due to Gust. Now, if lag IDG is 0, then the approximation routes specified by lag ID are used. So if this is 0 or blank, then the Gust parameters use the same lag parameters specified in the first lag ID field here. And then similarly, DMAT IDG is the same as DMAT ID except for the Gust. So this allows you to specify a non-default initial D matrix. And once again, in the vast majority of cases, you do not need to specify an initial D matrix. What ZAERO uses by default is good enough. And we do not need to go over any of these remarks. Okay, next is the dgust bulk data card to define the discrete Gust profile for the transient discrete Gust loads analysis. So we have an ID in the SID field. Next is type. This specifies the type of the Gust profile. So type can either be step, sine, 1 minus cosine, random, or table, or you can append a p onto the end of the name. So we have step p, sine p, 1 minus cosine p, random p, or table p. Now for type step, the Gust profile is a step function from tau 0 to tau equals infinity, representing a sharp-edged Gust. For type equals sine, we have one sine wave. So when tau is less than 0, the input is 0. When tau is greater than LG, it's once again 0, but when tau is between 0 and LG, then we have a single sine wave. For 1 minus cosine, similar, we have 1 minus cosine wave. So the advantage of the 1 minus cosine over the sine is it's continuous first and second order, whereas the sine, you've got a rapid, sharp change in the velocity. It's not continuous, whereas the 1 minus cosine is continuous in the time derivative of the input signal. Next, we have the random, where the discrete gust is a random number between -1 and 1 when tau is between 0 and LG. And then next we have type equals table, where we have an arbitrary gust profile where the user can define what that gust profile is. Tau is equal to t minus x naught over v, and then LG is defined in the LG field after type. And now for the P option, when you append the P to the type name, the gust profile is printed out on the standard output file. Next, we have the LG field. So for type step, LG is not used. For sine, 1 minus cosine, and random, LG is a real number, LG, which is shown in the equation. And then for type table, LG is an integer referring to the table D1 card for the user to define the arbitrary gust profile. WGV is the gust velocity divided by forward velocity, which represents a scale factor to the gust profile. X naught is the streamwise location relative to the origin of the aerodynamic model of the gust reference point. F max is the maximum frequency in cycles per second, or hertz, for the Fourier transform of the gust profile. And df is a further parameter for the integration. So if df is greater than 0, then the Fourier transform are calculated using the numerical integration, where df is the frequency step size. And if df is less than 0, then the fast Fourier transform technique is used, where the time step is defined to be df is 1 over n times dt, where n is the smallest power of 2, which satisfies this equation, where tn, t star, and dt are defined in the MLD time card. Now the interpolation method for interpolating the generalized aerodynamic gust forces from those computed at the reduced frequencies in the MK-AERO-Z card is defined by the symmetry of the flutter bulk data card. And the default for df here is 0.01 hertz. And then lastly, we have the NAP field. This is the order n of the pure time delay approximation e to the minus ts, which is approximated by 1 over 1 plus ts over n to the power n for the multi-zone discrete gust response analysis, where n is equal to NAP. This is only used if the GenGust bulk data card is activated and the discrete gust analysis is performed using the state space approach. Next, we have the MLD time card to define the transient time step. So we have an ID number. Next, we have T start, which is the starting time. T end is the ending time, and of course, T end must be greater than T start. DT is the time step. Out DT is a skip factor for the output. So every out DT time steps will be saved in the output file. So if you have a very small DT, for example, 0.001, so your simulation is running at 1000 hertz, but you're only interested in outputting at 100 hertz, you can set out DT to 10. Next, we have the print, which is a flag for the output. If print is less than 0, then there is no output. For print equals 0, then we output the numerical values of the time history on the standard output file. For print equals 1, we additionally print out the transformation matrix from the structural rigid body modes to the airframe states. And then for print equals 2, we additionally print out the state space matrices. And then the method field is not used. Next is the MLD print card for generating a data file, which includes the response parameters from the transient analysis. So ID print is the identification number. File name is the name of the file on which the data will be stored. Form is the format of the data, where only table is available. The PSD field is a character string, which can either be time or PSD. So for time, we output the time history data, and for PSD, we output the frequency PSD data. TS-PNT is the starting time for the printout. For the continuous gust analysis, TS-PNT is the starting frequency in Hertz. And obviously, TS-PNT must be greater than or equal to our T-start from the MLD time card. TE-PNT is the ending time for the printout. And for continuous gust analysis, T-end is the ending frequency in Hertz. The next field is a SOF. This is a character string, which can either be no, yes, or RFA. For SOF equals no, then the forces and moments at the structural grid points and the component loads are computed using the mode displacement method. If SOF is yes or RFA, then the summation of forces method is used. So for SOF equals yes, then the summation of forces method is used where the aerodynamic forces are obtained using the inverse Fourier transform. And for SOF equals RFA, then the summation of forces of method is used where we use the rational function approximation. And then lastly, we have an open-ended input label and I key. So label is a character string, and then I key is either a character string or an integer depending on label. So these jointly define the parameter of interest due to the transient maneuver loads. So each of these parameters will be output into the MLD print output file. And this is a table of what the label and I key can be to define the parameters. And this is much like the ASC Sensor 1 card. So we have state and D-state to output airframe state or the time derivative of the airframe state. And I key is a character string that matches one of the airframe states. Modal X, modal V, and modal G allow you to output the generalized modal coordinates, velocity or acceleration. I key is the integer of the index of the mode, which includes the rigid body modes. Then we have the grid options. So grid XT is displacement along the X, Y, or Z direction at a structural finite element grid, where I key is the integer of the identification number of the grid point. Grid XR is the rotational degree of freedom about the X, Y, or Z direction. Grid VT is the velocity of the grid. Grid VR is the rotational velocity of a grid. Grid GT is the second time derivative, the acceleration. Again, grid GR is the second time derivative of the rotational degree of freedom. Next we have force T, force T1, force T2, force T3. This is for the force along the X, Y, or Z direction of the structural finite element grid. And note the force needs the KGH matrix. So this can be imported. Remember, you can use the assign matrix to assign the KGH, the MGH, or the MGG. And ZAERO, if you import MGG or MGH, ZAERO will compute KGH for you. So T is the force, and then force R is the moment force of a grid. Now for these, the grid and the force cards, remember the degree of freedom here is the output coordinate system defined in your structure model. So with Nastran, remember you can define a grid. There's two different coordinate systems. There's the input coordinate system where the physical location of the grid is defined, and then there's the output coordinate system, which defines how the X, Y, Z directions are defined in the eigenvector. So these directions here are the output grid coordinate system. Next we have the load mod card. This is for defining the component loads from a load mod bulk data card. So I-key refers to the integer of a load mod card, so you can use these for wing shear, wing bending, etc. Next is the DMI. This is a parameter whose modal values are imported by the DMI bulk data card, so you could use this for modal stress or modal strain. EXTOUT allows you to refer to an EXTOUT bulk data card, where I-key is the integer of that EXTOUT bulk data card. So if you have a control system where you want to measure some value from that control system, or you have a complicated combination of sensors, and then you're measuring that from an EXTOUT card, you can do that this way. Cross PSD allows you to compute the cross PSD. So you refer to a cross PSD bulk data card, and then I-key is an integer of that identification number of the cross PSD card. This option is only active for the continuous Gust analysis, which we'll cover in the next section. Next is the PCH file for a punch file. So if you have a PCH file bulk data card, importing a Nastran punch output file, you can refer to that through this option. And then we have delta X, delta V, delta G to measure the control surface deflection, rate, or acceleration. I-key is an integer referring to the index of the AE-surf-Z card listed in the surfset bulk data card. Next, we have the GenGust bulk data card, which allows you to alter the gust field. So remember, by default, we have a vertical gust. So ID is an identification number. IDMK refers to an MK arrow Z card. SIM must either be SIM, ASIM, or anti, and of course this must match the SIM, ASIM, or anti in the MK arrow Z card. End zone is the number of gust zones, which by default is 1. Alpha is the gust angle of attack in degrees, and remember the default's vertical gust, so that's 90 degrees. Beta is the gust side slip angle in degrees with a default of 0. Shift is an option to shift the gust control point. So this is a fraction of the box chord length to shift the control point locations where the downwash of the gust is applied. So this can be a real number between minus 0.5 and positive 0.5. The default is 0, so the control point is not shifted. And then the option field is an option flag integer to select the option for specifying the gust zone. Next, we have an open-ended input made up of xg0 and ID pan. So for xg0, this is the gust reference point of the ith gust zone with respect to the origin of the aerodynamic model. This is only used for the discrete gust analysis using the state space approach. For the hybrid and frequency domain approach, discrete gust analysis, the gust reference point specified in the dgust card is used. And then for option equals 0, the ID pan is the identification number of a pan LST1, pan LST2, or pan LST3 card whose specified aerodynamic boxes are excluded from the ith gust zone. If option is greater than 0, then ID pan is a real number to specify the x location of the end of the jth gust zone. So in this case, the remaining ID pans are not used. So this is an easier option for inputting which boxes belong to which gust zone. So you would set option equal 1, and then if you want to split your model into 3 gust zones, you just have the x coordinate, which is the boundary between the first and second gust zone, and you would specify the first x coordinate in ID pan 1, 1, and then for the second gust zone, you would specify the second x coordinate, and then for the third gust zone, the last x coordinate. Next is the plot time card, which allows you to generate an ASCII file for the post-processing of transient response analysis. So ID plot is the identification number. ID MLD is the identification number of the MLoads. E-loads, G-loads are nonlinear flutter, so in our case this would refer to the G-loads card. TS is the starting time for plotting, and TE is the ending time, and then NDT is a skip factor. So this NDT is combined with OutDT from the MLD time bulk data card. So the final time step for the plotting output is NDT times OutDT times DT. Next, you specify the type of the plot time output. For type equals force, we store the flight loads that are obtained by the mode displacement method in terms of Nastran force and moment bulk data cards at the structural finite element grid points in an ASCII text file. You can then use this file to combine with the Nastran model and run Nastran to obtain a more detailed stress analysis by performing a static structural analysis. For type force SOF, this is the same as type force, except we use the summation of force method, with the time domain aerodynamics being obtained by the inverse Fourier transform. And then for force RFA, we use the summation of forces, but with the time domain aerodynamics being obtained using the rational function approximation technique. This option is only active for the M-loads, E-loads, and G-loads disciplines with the state space approach. Now, using these options will cause ZAERO to compute the forces at all finite element grid points. So for a large structural model, this may significantly increase the computational time. Next, we have type equals elastic. This stores the time history of the deforming aerodynamic model. This deformation includes only the structural rigid body and elastic deformations. So this it would be for a plot file to visualize the time history of the deforming model. Type no rigid is the same as elastic, but it excludes the rigid body modes. So this could make for a nicer animation if one of your rigid body modes is not stable. Next we have type UCP to plot the unsteady CP. So if the form, which is the next field, equals output 4, then this stores the time history of the pressure coefficients on the aerodynamic boxes in the output 4 format. Now the number of rows in the output 4 matrix is the number of aerodynamic boxes, and the number of columns is the number of time steps. And for form does not equal output 4, for example, if form equals tecplot, then it's the same as type no rigid, except the pressure coefficient contour is also displayed on the deformed aerodynamic model. So using this option, you can get a plot of the deforming aerodynamic model, and at the same time, you can plot the pressure coefficient contour on that model. Next, we have form, which is the format of the data. So this could be tecplot or output 4, and I believe there's are additional options available as well. Scale is a multiplier to the structural deformation, which by default is 1. So if you want to amplify the deformations that you see just for visual purposes, you can do that. And then file name is the name of the file. Arrow name is only used when the form is patran. Okay, next we'll look at some numerical examples for the discrete gust. So this is an open loop discrete gust analysis for a generic business jet. And this generic business jet is one of the standard ZAERO test cases. So the purpose here is to demonstrate the open loop discrete gust response analysis of a generic business jet using the frequency domain, the state space, and the hybrid approaches. And we're going to generate a state space plant model with the aileron and Gust as input to design a gust load alleviation control law. So this is the structure model on the left. For the fuselage, we have just a simple beam model. And then for the wing, we have a more detailed wing box. And then our engine and tail are just connected to the fuselage here. For the aerodynamic model, Actually, this is from the plot surf card. You can see we have the aileron deformed here. So we have our aileron, we have the wing, we have a detailed fuselage and engine nacelle, and then there's a ZAERO 7 representing the pylon connecting the engine to the fuselage, and then we have our vertical and horizontal tail. And obviously this is a half-span model. So we have two control surfaces, the aileron, which we saw in the last slide, and then we see again here, and the elevator. This is our transfer function for the actuator for both the aileron and the elevator. So for the aileron, this is the AEserv-Z card. So we've named it aileron. This is a half-span model, and we have symmetric control surfaces. So for purposes of the gust load alleviation control law, we have a symmetric aileron controller. So the Cord 2R bulk data card here defines the hinge line axis. So the minus 1001 means to use the z-axis of this Cord 2R card. So the z-axis of the Cord 2R card defines the hinge line here. The 5101 refers to the pan-LST. This defines the boxes. So we use the pan-LST1 card, which is the easiest for defining a control surface. So that just specifies this box ID and this box ID, and then we get this square rectangle of boxes here to define the aileron. And then lastly, the actuator. You can see that this number here, the A0 is here, A1 is here, and then A2 is here. And then lastly, for the elevator, we have the Cord 2R card. Once again, the z-axis of this defines the hinge line, and then the pan-LST1 card defines the boxes that make up the elevator. And then we have the same actuator. Now note, even though we have the same transfer function for both the aileron and the elevator, we need unique actuator bulk data cards because the ID number of the actuator will be referred to by our closed loop controller and control system. So you are not allowed in the AEserv-Z card to refer to the same actuator card. If this was 1702 referring to this actuator, that would not be allowed because one actuator bulk data card is not allowed to be used by two different AEserv-Z cards. Next, we have our sensors. So once again, I recommend the sensor 1 option because it's easier to read. So you can see straight away just by looking at the bulk data card, the ASE sensor 1 with ID 2051 is a grid acceleration in the Z direction at grid number 293. So this is grid 293. So this is an accelerometer in the vertical direction. This grid will be used for the controller design, and then the remaining sensors here are only used for output. Okay, next we're going to look at the frequency domain approach for the open loop GBJ. So this is our Gloads card. Our con ID refers to the ASE controller, and this is the open loop model, so we only are referring to a surf set and send set. There's no closed loop control law. So the ASE controller card here, we have referred to the surf set 1125 and then the send set 1126. This is a typo. This should be 1126. Meanwhile, the Gloads card refers to the flutter card with ID 10. This refers to the fixed MATM card to define the flight condition. So remember, for a time domain analysis, the fixed card only has one flight condition. If there are more specified, then the first one is used for the analysis. Whereas for a flutter analysis, you'd have multiple altitudes listed here to do the sweep. but with the time domain analysis, you can only perform that at one flight condition. The fixed MATM refers to the MK-AERO Z card. Note here that our reduced frequencies are going higher than typical. That's because with the Gust analysis, you need higher reduced frequencies because the Gust will excite those higher frequencies. But we do have the negative option here in the MK-AERO Z card. Remember, the negative option increases computation time, but tries to get more accurate results at these higher reduced frequencies. The flutter card also refers to the tab DMP card. I'm assuming it's specifying 3% structure damping. Okay, moving on with the Gloads, the RAAID field is 0, which specifies the frequency domain approach. The states field is blank, so we're not converting any rigid body states to airframe states. The ID Gust refers to the dgust card with ID 20. The time refers to the MLD time card with ID 10, and MLD print refers to the MLD print card with ID 10. And actually, we have multiple MLD print cards, all with ID 10. Also, we're going to save the frequency domain data from the Gust. So the file freqqhj.dat saves the interpolated generalized aerodynamic forces for the Gust at each frequency step of the K values in the MK-AERO Z card. Now, as long as this frequency step is not changed, this file can be acquired for different Gust profiles or for the hybrid approach. So we'll see that on the later subcases. This is the discrete Gust profile. So we have a 1 minus cosine Gust profile where LG is 0.19091. So our Gust profile is given here. It's WGV over 2 times this 1 minus cosine, and tau is T minus X naught over V. The fixed MATM card defines the flight condition to be Mach 0.85 with an altitude of 30,000 feet. So with the standard atmosphere, this corresponds to a velocity of 846 feet per second. Now, if we assume a physical gust length of 161.4 feet, then LG is 161.4 divided by 846, which is 0.1909. So that's the LG field here. Now, if we want a gust velocity of 50 feet per second, then WGV is 50 divided by 846, which is 0.059. X naught is minus 10,150 inches, so that the gust hits the aircraft nose at a time of X naught over 846, which is 1 second. And the maximum Kmax in the MK-AERO Z card is 5. So Fmax is equal to Kmax times V over ref C over 2 divided by 2 pi, which is 57.27 hertz. Therefore, there are Fmax over dF, or 5,727 frequency steps, because Fmax is blank here. Next, we have the ASE controller card. So we have the surf set and send set. In the surf set, we just refer to the elevator and aileron, and then the send set lists out our sensors. This does not refer to a TF set card, so there's no control system, so this is an open loop analysis. So the purpose here allows us to generate a plant model, which we'll export to MATLAB, and then we can do a control law design in MATLAB, and then import that controller back for a closed loop analysis. Next, we have 2 MLD print cards, both with ID 10, and this is allowed. So first, we want to compute the loads by the mode displacement method. So the SOF field is no in the MLD print card, and our file name we have MD. So we have our grid acceleration, and then we have 3 load mod cards. And then next we're going to compute these loads by the summation of force method. So the SOF field is equal to yes. We did not repeat the grid acceleration because the grid acceleration is not dependent on the SOF option. The SOF option only applies when you're computing loads. So the component loads that we have defined here, we have Z shear, and this is all on the wing. So we have the shear of the wing. Then we have X moment. So we've got wing bending, and Y moment. Y moment would be the wing bending, and then X moment would be the wing torque. So the set 1 here lists out all of the grids on the wing. So with the mode displacement method, only these grids are used. The boxes that we have defined are not used. But with the summation of forces method, the grids are used for the inertia force, and then the boxes defined by the MNStack card are used for the aerodynamic forces. And then lastly, we have this chord to our card to define the coordinate system where these loads are computed. Next, we'll be looking at the output file from the analysis. So the frequency domain approach first prints out the 1 minus cosine Gust profile in the output file, which looks like this. So notice it says the discrete Gust profile specified by the Gust card with type OMCOS. So this is our 1 minus cosine. Then it applies the Fourier transform to transform the above time domain Gust profile to the frequency domain and prints out the real part and imaginary part of the frequency domain Gust profile as shown here. So this is our Gust excitation in the frequency domain. Then next, the frequency domain Gust profile T of I omega is multiplied by the generalized aerodynamic Gust column QHG of I omega given by this equation. So G of I omega is just QHG of I omega times T of I omega. So G of I omega for the first 10 modes are printed out in the output file as shown here. So this is our G of I omega. The first is the real part, and then the second one is the imaginary part. And then we have a note: the above function should decay rapidly at high frequency, otherwise increasing Fmax and max K is recommended. So remember, in theory, the frequency here should go out to infinity. To do the Fourier transform, you have to integrate to infinity. Obviously, we can't compute out to infinity. We have to stop somewhere. So that's the purpose of the Fmax field in the Gust card. So you want the Gust to decay out to about 0 so that since we're chopping off everything greater than 57.27 hertz to infinity, this should all be 0 because we're chopping it off and we're not including it in the integration. So if this is still, if it's not decayed out to 0, then obviously you're chopping off important signal here that's non-zero. But since it does decay down to 0, everything that we're chopping off greater than 57 hertz is practically 0, so we can ignore it when we integrate back from the frequency domain to the time domain. And that's the purpose of this note here. So we're going to review here the computational procedure in the frequency domain approach. So the frequency domain approach combines the generalized structural and aerodynamic force matrices to construct this equation for the plant model. Now XP is made up of Cc and delta, and that's the state vector of the plant model. Cc is the structural generalized coordinates, and then I omega times Cc would be the velocity. Delta is our actuator states. MHH is the generalized mass matrix. Now since we have 30 structure modes and 6 actuator states, the number of states of the plant model here is 66. And the time domain solution of the plant state vector is obtained by applying the inverse Fourier transform shown here. So the QHG of I omega at each frequency step can be saved using the entry save in the Gloads card, which we've done, and then retrieved for a different t of I omega. And the I omega minus a of I omega inverse, that's shown here, at each frequency step can be saved using the entry save FRQ, and then can be retrieved for different QHG. And I misspoke earlier. We're using the save FRQ option, but we're not using the save option in the Gloads card. So next we have the component loads. So we're reviewing that once again here. For the mode displacement option, which we've done, then L of t, the loads, is computed using this equation. So Lg of t is the inverse Fourier transform of kgg times c of I omega, or kgg times phi, which is our mode matrix, times c of I omega. And of course, you don't want to import the kgg matrix into ZAERO because for large structure models, this could be a very large matrix. Instead, you want Nastran to compute kgg times phi for you, which is the kgh matrix. So I would recommend importing the kgh matrix. Now, if you don't import the kgh matrix, instead you import the mgh matrix, then ZAERO computes kgh for you by mgh times omega squared. And then if you just import the mgg matrix, then we have mgg times phi times omega squared. Now Lg, shown here, is the loads integration vector specified by the load mod card from the set 1 card to define the grids. So this integrates the G set forces to the sectional loads. Now for the SOF option, we do an integration on the aerodynamic boxes. So then we use LK, so the times SKJ, and then notice in here we have, instead of going through the KGG matrix, we're going from the modes directly to the boxes for the AJH and AJC matrices. And then we're integrating from these boxes. We use the SKJ matrix to convert the CP to forces, and then the LK integrates the boxes to a force. So the LK is the loads integration vector specified by the load mod card, and this is through the pan LST field of the load mod card. That defines the boxes which define the load. So that integrates the K-set aerodynamic forces to sectional loads. SKJ is the integration matrix to convert the aerodynamic pressure coefficients to K-set forces, and then AJH, AJC, and AJG are the matrices containing aerodynamic pressure coefficients due to the structure modes, control surface modes, and gust profile. And of course, phi is the G-set mode matrix, and phi C is the matrix containing the G-set kinematic control surface modes. And then we do still have the inertia loads computed lastly here. So that goes through the LG. So we integrate on the along the grids, the structure grids. So now we'll compare these options. First we'll look at the mode displacement. So the mode displacement method requires many modes for the convergence of component loads. So what we're doing here is comparing the mode displacement method using 30 modes, 50 modes, and 100 modes. Now with the grid point acceleration, 30 modes is already enough. You can see the 30 modes, 50 modes, and 100 modes all lie on top of each other. We get the same answer. So for just measuring grid point acceleration, 30 modes is adequate. But now when we go to looking at loads, we've got wing root shear, wing root bending moment, and wing root torque. You can see that the curves change when going from 30 modes to 50 modes to 100 modes. This indicates that when the airplane is initially hit by the gust, 30 modes and 50 modes and 100 modes all give a different answer. So we don't have a converged solution, so that the mode displacement method can't give a correct answer yet, even up to 100 modes. The structure is being excited in such a way that the modal response doesn't capture the loads correctly when using the mode displacement method. Now, after the initial kick, you can see that all three options go back to the same answer. So our response here after the initial kick is most likely accurate after this initial response. But we can't tell, is 100 modes enough yet? We don't know, because comparing 50 modes to 100 modes, the answer is still changing. So 100 modes may not be a converged answer yet. It may not be the right answer. So now let's compare with the SOF option. So the SOF method requires much fewer modes than the mode displacement method for a convergence of the component loads. So now when we plot the 30 modes, 50 modes, and 100 modes on top of each other and compare the wing root shear, wing root bending moment, and wing root torque, you can see that all of the answers agree with each other. So now, only using 30 modes, we're already getting the correct answer, because when we increase the number of modes, the answer doesn't change. So this indicates that we do have a converged answer. So we recommend using the SOF method to get the the correct answer. But however, do remember the SOF option does increase your computation time. So now we'll compare the wing root bending, wing root torsion, and wing root shear, compare the mode displacement and the SOF. So we have the mode displacement using 100 modes and the SOF of 30 modes, and you can see that the initial kick here, the answers do not agree with one another. But then as time goes on and the high frequency excitation dies out, then the answers do converge to the same answer. So this indicates that even with 100 modes, the mode displacement method is not accurate yet. So we would need even more modes for the mode displacement method. So the mode displacement method for this high frequency dynamics at the beginning is not accurate, and it's not a converged solution. Okay, next let's move to the hybrid approach of the open loop GBJ model. So with the hybrid approach, the Gust aerodynamics will be solved in the frequency domain, whereas the normal modes and control surface modes will be computed in the time domain using the RFA. So now the Gloads card refers to a MNStack card with ID 20. So this MNStack card refers to the aero lag card to define 15 aerodynamic lag routes, and then we have our approximation constraints defined here. Now the hybrid approach computes the time domain generalized aerodynamic forces as shown here. So we have our Gust aerodynamics specified in the frequency domain. We perform the inverse Fourier transform to give us our Gust excitation in terms of a time vector. Then it solves the state vector by this equation here. So we have x dot plant is a plant times x plant plus this excitation vector. So this FG here is pre-multiplied by MHH inverse. So our plant is made up of C dot, XA is the lag states, and then delta, delta dot, and delta double dot are the actuator states. And the matrix AP is a real matrix constructed by the structural generalized mass, stiffness, and damping matrices, as well as the RFA matrices of QHH of I omega. Now the component loads now will be computed in this way with the hybrid approach. The mode displacement method is just LG transpose times MGG times phi times omega squared. And remember, this MGG times phi times omega squared can be replaced by KGH. So this is just LG transpose times KGH times C of t. The SOF method is the same as that of the frequency domain approach, which we saw a few slides back. And then the RFA method L is computed by the aerodynamic forces minus the inertia forces. So the inertia forces is LG transpose times MGG times phi times c double dot. So this is MGH. This is MGC times delta double dot. And then our aerodynamic forces here, we have the aerodynamic CP as a function of c dot, c double dot, delta, delta dot, and delta double dot. So this computes the forces on each box. And then with the gust, we're going through the inverse Fourier transform here. And once again, we're getting our gust forces on each box. And then lastly, our lag states contribute to the CP on each box. Once we have the CPs on all the boxes, we then pre-multiply by SKJ to convert that to the K-set forces, and then use the LK matrix to integrate those forces. Now we'll compare the hybrid and the frequency mode displacement. So you can see the mode displacement method with both the hybrid and frequency agree with each other. We just have a slight time shift here, but the time shift doesn't really matter. The final response is the same between the two solution options. So this indicates that our RFA performed on the normal modes and control surface modes is a good RFA because we are agreeing with the frequency domain analysis. Next, we'll compare the wing root shear, wing root bending, and wing root torsion moment between the mode displacement, the SOF, and the RFA options using the hybrid approach. So we recommend the SOF option, and when we look at the initial response, the RFA and the SOF options agree pretty well, but the mode displacement method, as we've seen before, is not as accurate. Once we move on in time, the mode displacement and SOF options begin to converge and agree with each other, whereas the RFA has some difference here as time goes on. So we would recommend the SOF option in general, but if you're exporting your plant model, then and you're measuring your loads from the state space model, essentially you'd be using the RFA option. Next, we'll compare the wing root shear, wing root bending, and wing root torsion. Compare the hybrid and frequency approaches using the SOF option. So once again, the hybrid and frequency computation methods agree with each other when we use the SOF option. And then lastly, we'll use the state space approach for the open loop GBJ plant model. So now we use a negative sign to refer to the MNStack card. So this triggers the state space approach for the Gust. And then also we're going to output the state space plant model to file gbj plant.dat for control law design. And then this is our RFA for the gaffs of the Gust. So once again, we have 15 lag roots. And now with our approximation constraints, we want to apply different constraints on the Gust. So for the normal modes and control surface modes, we have DA1 is 2, DA2 is -1, so no constraints there. And then we're splitting the number of column partitions into 2. So the first column partition is all of the normal modes and control surface modes. And then the second partition, column 33, is the Gust. So we have 30 normal modes, 2 control surface modes, and 1 Gust zone. So that 33rd column here is the gust zone. Now for the gust aerodynamics, we're setting the A2 parameter to 0. So remember, for the gust, A2 must always be set to 0. ZAERO does not automatically do this. You must do this as a user. So we're illustrating that here. For the gust lags, we're using only 5 lag roots for gust. So we have a different number of lag roots. This is to avoid an overfit, so we're using fewer lag roots. And then additionally, we are removing reduced frequencies 3, 4, and 5 from the RFA. So we're doing that through the K-list field in the MNStack card. So that's removing reduced frequencies 13, 14, and 15 from the list, which correspond to values of 3.0, 4.0, and 5.0. Now, for illustration purposes, we're also showing how you can set different constraints on the box level as compared to the modal coordinates, but these constraints are the same as we have defined over here. So you actually don't need these two cards. If you don't specify constraints for pressure coefficients, it will reuse the same constraints you have here in the modal RFA. But we're just illustrating over here how you can do that. Okay, next we'll look at the spiral characteristics of the gust gaps at various reference points. So the severity of the spiral characteristics of the gust gaps depends on the selection of the gust reference point xg0. This is because the gust gap is a function of e to the minus I omega times x minus xg0 over v, where x is the control point on the aerodynamic boxes. Therefore, for those aerodynamic boxes located far away from xg0, the spiral characteristics are very severe. So the box highlighted in red here is the xg0 that we've selected for the current case, where this is an xg0 of 690, which is right here. So you can see we've selected basically the midpoint of the wing as our gust reference point. So this gives us the least spiral characteristics. But now if we compare the first mode to an x0 of 0, if this is our gust reference point, you can see that we have a spiral developing here. Whereas here, we don't have a spiral developing yet. So this should be an easier fit for the RFA than this spiral. In the same fashion, if we choose an xg0 of 1200, so that's back here, we also get a spiral. Now if we choose an x0 of minus 1000, which is way up here, the spiral is so severe that we really can't even see it. It goes something like that. So we would actually need more reduced frequencies here to actually see this spiral. And obviously this is going to be very hard to fit for the RFA. And we have the same illustration for the second mode, third mode, and fourth mode. The fourth mode here is pretty easy to see. You can see we've got a spiral here. We have a spiral here. This spiral, once again, is very, very spirally. And then for the x0 of our chosen case, 690, this is our curve, which should be easier to fit. So the upshot here is you want xg0 to be near the middle of the wing, so that this x minus xg0 is a small value for a majority of the boxes. So the best xg0 is located at the middle of the wing root chord. So this is specified in the GenGust card. So if you look in our input, we have an xg0 of 690. Now if we take a look at the gust lag RFA as compared to the computed, you can see that we have a pretty good fit for each of the modes. So now we'll look at the component loads computed by the state space approach. For the Gust loads analysis, the state space approach is not recommended due to the inaccurate RFA of the Gust graph. However, the state space approach is used for generating the plant model using the ASE out card for the Gust load alleviation control law design. So you want as good of a Gust approximation as possible, because we're going to be using this Gust approximation to design the Gust load alleviation control law design. However, in your final analysis, you want to go back to using the frequency domain or the hybrid Gust analysis to make sure that you still have good results. Now, using modern control law design methods such as H-infinity control scheme, a good, robust control system can be designed that can handle high uncertainties in the plant model to provide a good Gust load alleviation capability. So our first row here, we have the open loop GBJ transient response computed by the hybrid and the state space approaches for parameters of interest using the SOF option. So if we compare the state space and hybrid, we actually get a very good agreement. So our Gust RFA is actually pretty good. Next, we'll use the RFA option, comparing the state space and hybrid options, and you can see we got a pretty good agreement. So the RFA option, when you export the plant model from ZAERO and then you do your simulation in MATLAB and look at your loads, this is the loads you'll be seeing, is the RFA option of the state space model. So next, let's say we've designed our controller, so now we're going to move on to the closed loop GBJ. So with our exported plant model from the previous slides, we've designed a Gust load alleviation control law, and now we're importing that into ZAERO. So we have our ASE controller card is now referring to the TF set and CNTC set. So our control law is a MIMO SS. So we have our one sensor used in the control law design feeding into the MIMO SS. This now feeds back to our aileron actuator for the Gust load alleviation. And then, since we're doing a frequency domain approach, the RAAID field of the G loads is 0. And now you can also see we're acquiring the frequency domain Gust because we saved that in the open loop analysis. But that part hasn't changed, so we can now acquire that for a faster analysis. This is our control system. The controller has one input and one output, and it has 50 states. And the ABCD matrices of the controller are imported by the DMI bulk data card. You could also import them through the assigned matrix card. So our DMI card here is defined here. So our ABCD is a 51 by 51 matrix because we have 50 states, one input and one output. Our TF set card here refers to the MIMO SS. So this MIMO SS refers to the matrix name KS. And then these remaining cards connect the sensor to the MIMO SS and then connect the MIMO SS to the actuator. So now we'll look at how well our controller works. So with the closed loop and open loop GBJ transient responses computed by the frequency domain approach for acceleration at grid point 325. So the controller here can reduce the maximum acceleration at the wingtip from 1,150 feet per second squared to 900 feet per second squared. So the open loop is in red, the closed loop is in black. So you can see the initial response from the Gust. The open loop is up here and down here, and the closed loop has reduced that acceleration to here and here. Additionally, as we move further out in time, you can see that the higher frequency dynamics have been suppressed and the closed loop is dying down quicker than the open loop. Now if we look at our aileron deflection angle, you can see that the aileron was working actually quite hard. We've hit at max positive 6 degrees and about minus 7 degrees. And the frequency of the aileron here is about 5 hertz. The dominant frequency, I should say, or the low frequency. Here's a gust response animation using the plot time bulk data card. So we have our plot time card refers to the Gloads card. So we're going to animate that here.